All right, let's go ahead and get started. I want to welcome you to this worksheet. This is percent composition and empirical formula. You are going to need a calculator and a periodic table for this one, so if you don't have those, get those handy. So let's take a look at number 1. It says, what is the percent composition of sodium carbonate? So what do we mean by percent composition? Well, what we mean is we're going to have to determine the percent by mass of each of the elements that are in sodium carbonate. And sodium carbonate is Na2CO3. Remember, I got that by simply saying, well, sodium is the first column. It has a charge of +1. Carbonate is a polyatomic ion. It has a charge of -2. Remember, when I do the switch, I get this, Na2CO3. So now that our job is to determine the percent composition for each element. Let's start with sodium. So the percent by mass for sodium is equal to the mass, or the atomic weight of sodium, which is 45.98, divided by the total. Now I've added up the total here. It's 105.99. I got that by multiplying sodium by 2 because there's 2 of them, adding to that carbon, and then adding to that 3 oxygens because there are 3 of those. So we get 105.99 grams total. So I'm going to divide everything by this number. 105.99 is my total. So let's start with sodium. Percent by mass of sodium is 45.98 divided by the total of 105.99. It's percent, so we'll multiply that by 100, and we get a 43.38% for sodium. So that's sodium. Let's take a look at carbon now. Carbon has a mass of 12.01. There's only one of them, so I don't have to multiply that by anything. But I do have to divide by the total of 105.99. I'm going to multiply it by 100 because it is percent, and now I get 11.33%. And the last one is oxygen. I want to know the percent of oxygen, so I'll add the 3 oxygen. 16 times 3 is 48. I'll divide that by 105.99 times 100, and I get 45.29%. Just to do a quick check, you should add these 3 numbers up, and they should be very, very close to 100, if not exactly 100. All right, let's take a look at number 2. What is the empirical formula, and how is it different from the molecular formula? The empirical formula is the lowest whole number ratio of atoms in the compound. The molecular formula shows the true number of atoms in the compound and is a whole number multiple of the empirical formula. It must be whole number. Let's look at number 3. C6H12 is an actual compound. It's called hexane. But we can divide both the 6 and the 12 by the largest common multiple, which is 6. And when I do that, I get CH2. So the empirical formula for this molecular formula would be CH2. For Fe2O3, there's not really much we can do because one of these is an even number, the other one's an odd number. So it remains Fe2O3. So both the empirical formula and the molecular formula, Fe2O3. Now for K2C2O4, we can divide everything by 2, of course. That's the greatest common multiple, and I get KCO2, and that is my empirical formula, the lowest common multiple formula. Let's look at number 4. It says a sample of a compound is 50% sulfur and 50% oxygen by mass. So we know that only these 2 elements, sulfur and oxygen, are involved. They want to know the empirical formula, the lowest whole number ratio formula. So let's start with sulfur. What I'm going to do actually is a kind of a neat little trick. What I'm going to do is, even though I'm starting with percentages, I'll assume a 100-gram sample. I can assume any size sample I want. Let me just make it easy on myself and make it a 100-gram sample. So if 50% by mass is sulfur, that means that that's 50 grams of sulfur and 50 grams of oxygen, right? 50 grams sulfur, 50 grams oxygen. And so now what I'm going to do is convert those to moles, because in an empirical formula, I'm looking at mole-to-mole ratios. So I'll divide 1 mole of sulfur by 32.07 grams, and notice that grams of sulfur and grams of sulfur are going to cancel away, just like grams of oxygen and grams of oxygen will cancel away here. But I'm dividing by a different thing because oxygen doesn't weigh the same as sulfur. It only weighs 16 grams per mole. And so now I'm going to actually divide. 50 divided by 32.07 is 1.559, kind of a strange number. And 50 divided by 16 is 3.125, another strange number. Remember that the empirical formula has to be the simplest whole number ratio. Whole number, the key here. So to get to a whole number, what I'm going to do is to look to see which one of these 2 moles is the smallest and divide both of them by that number. In this case, it's the 1.559. I'll divide 1.559 by 1.559, and get 1 mole of sulfur, or 1 sulfur. 3.125 moles of oxygen divided by 1.559 is very close to 2. Very close to 2. So it's a 1 to 2 sulfur to oxygen ratio in the empirical formula. Now that's not to say that that's necessarily the molecular formula. It may be, but it may not be. The molecular formula may be S2O4 or S3O6, or I can go on infinitely. But the point is that the empirical formula is going to have a 1 to 2 sulfur to oxygen ratio. Empirical formula, SO2, and I'm done with number 4. Let's look at number 5. Number 5 says that a compound is 52.9% aluminum, the rest is oxygen. What is the empirical formula? Well, the first thing I'm going to do is I'm going to assume a 100-gram sample. So remember, if you're given percentages, assume a 100-gram sample to make things easier on yourself. So that means I've got 52.9 grams of aluminum, and the rest, 100 minus that, would be 47.1 grams of oxygen. So I'll start with those masses and convert both to moles. For aluminum is 26.98 grams per mole, and oxygen is 16.00 grams per mole. And now that's going to allow me to convert both of those to moles. These are the numbers that I get: 1.961 moles for aluminum and 2.944 moles for oxygen. Obviously not whole numbers, not simple whole numbers, that's for sure. So how do I convert those to whole numbers? Well, I take the lesser of the two, in this case is the 1.961, and divide by that number for both of these, not just one, for both of these. Obviously one of them is going to come out to be 1 mole. It's the aluminum in this case, the smaller one. I've got 1 aluminum, and I've got 1.5 oxygen. So I've got a problem here because of the fact that an empirical formula is a simple whole number ratio. It can't be 1 to 1.5 aluminum to oxygen. How do I remedy this problem? I multiply both by 2. So I say times 2 for the aluminum, times 2 for the oxygen, and I get 1 times 2, 2, 1.5 times 2, 3 oxygens, okay? So the ratio of aluminum to oxygen is Al2O3. That's the empirical formula for aluminum oxide, all right? That's number 5. Let's look at number 6. Number 6 says the empirical formula of a compound is P2O5, right? Its gram formula mass is about 284 grams. What is the molecular formula? So they're giving me the formula mass, they're giving me the empirical formula, but they're asking me for the molecular formula. How do I go about this? Well, what I'm going to do is I'm going to take the empirical formula, in this case P2O5, and I'm going to determine the mass of that empirical formula, not knowing if it's also the molecular formula just yet. So I'm going to say phosphorus, which is 30.97 grams per mole, times 2, plus oxygen, which is 16.00 grams per mole, times 5, and we're going to add those up. We get 141.94. 141.94 is the mass of the empirical formula, but they're telling me that the gram formula mass for this compound is not 141.94, it's 284 grams. So the question then becomes, what is the ratio of this 284 gram number that they're giving me to the 141.94 grams that I've calculated from the empirical formula? Well, it's a 284 divided by 141.94 is about 2. So the ratio of the molecular to the empirical formula is 2. So what I'm going to do to arrive at the molecular formula is I'm going to take the empirical formula, which is P2O5, and just multiply it by 2. And when I do that, I get P4O10. So the molecular formula is P4O10. Remember, the empirical formula was P2O5, but the molecular formula, P4O10, and I figure that out based on the fact that the gram formula mass was double the 141.94 that I calculated. All right, let's go to the last one, number 7. Number 7 says this. It says a sample has a mass of 43.0 grams. Its percent composition is 40% oxygen, 6.7% hydrogen, and 53.3% oxygen. Its gram formula mass is about 180 grams. So that'll be an important piece of information right there. They want to know both the empirical and the molecular formulas for this compound. All right, let's get to work. So first, we're going to assume a 100-gram sample, right? It says the sample has a mass of 43 grams. For us, it's not even relevant. I don't even need to do that. I'm going to assume a 100-gram sample because of the fact that they're giving me percentages, so I can assume any sample size that I want. I don't have to take 40% of 43, 6.7% of 43, and 53.3% of 43. I can assume any sample size I want since I've got percentages. So I'll assume a 100-gram sample. So I'm going to say 40 grams of copper, 6.7 grams of hydrogen, and 53.3 grams of oxygen, respectively, times I'm going to convert to moles. 1 mole of carbon, 12.01 grams of carbon. So these are going to cancel, just like that. 6.7 grams of hydrogen, or excuse me, 1 mole of hydrogen, 1.01 grams of hydrogen. This is going to cancel with this, and finally, this is going to cancel with this. So now what I'm going to do is convert to moles, but look at the numbers that I get. 3.31, 6.634, and 3.331. Ugly numbers, certainly not simple whole number ratios, right? So how do I get to the simple whole number ratio? Find the smallest of the three. It's obviously either this 3.331 or this 3.331. Doesn't matter, because I'm going to divide all of them by 3.331, and when I do that, I say this one right here, 3.331 divided by 3.331 is 1 carbon. 6.634 divided by 3.331 is 2 hydrogens. And 3.331 divided by 3.331 is 1 oxygen. So that's telling me that the ratio of carbon to hydrogen to oxygen is 1 to 2 to 1. So the empirical formula is CH2O. Now that I've got the empirical formula, I want to know the weight or the mass of that formula. When I add these up, I get 12.01 plus 2 times 1.01 plus 16, and I get this number 30.03. Now let me compare that to the gram formula mass they're giving me. They give me 30. They're giving me 180. Well, 180 is 6 times bigger, about 6 times bigger than the 30.03 that I calculated for the empirical formula. That means the molecular formula must be 6 times bigger than the empirical formula. The empirical formula is CH2O, then the molecular formula is C6H12O6. That's the correct answer. I'll see you on the next one. Thanks. Bye-bye.